Okay, this is AP Calculus, section 3.10, the last section of chapter 3. It's called Economic Applications. And basically what we're going to be looking at is, this is still going to be optimization type stuff. You're still trying to maximize or minimize a situation. It's just really problems involving money with economic stuff. So just some different applications of that. Profit, revenue, cost, trying to minimize costs, things like that. Okay, so some basic terms or terminology stuff in this section. First of all, typically in an equation when you see X, it's going to be the number of units produced or sold, although that's not always the case, but typically that's the case. We will see one example today where we're going to define X differently. But typically when you're given a revenue equation or cost equation, that's what X represents. When you see a lowercase p, that's used to represent the price of one unit, when you sell it or to make it, basically, or what you're selling it for. Big R usually stands for revenue, and revenue is always the number of units sold times the price you're charging per unit. So revenue is equal to X times P. A capital C represents total cost for producing X units. When you see C with a bar over it like this, that's the average cost per unit. To get the average cost per unit, we take the total cost of producing units divided by the number of units, and you get the average cost per unit. So for example, if I produced 30 units and it cost me $300 to produce them, well, I would take the $300 total cost divided by the 30 units, and I'd get that it cost me $10 per unit. Okay, so that's average cost per unit. All right. So a lot of times you have to minimize your average cost, or try to do basically try to minimize average cost is all you would be doing with something like that. So the big thing you have to remember is you have to take your cost equation and divide it by X before you try to find the derivative. Profit is revenue minus cost. Okay. Capital P typically is used to stand for profit. Remember again the difference there, lowercase p is the price for one unit, capital P is a profit equation. If you're asked to find anything to do with marginal profit, marginal revenue, or marginal cost, okay, that is the extra profit from selling one more unit. dP over dx approximates that. Okay, so basically it's the change in the profit over the change in one unit, or the change in X. Remember, X is the unit sold. Okay, so if we get dP over dx, we've got marginal profit. dR over dx, by the same reasoning, would be marginal revenue, extra revenue from selling one more unit. Marginal cost, dC over dx, the extra cost of producing one more unit. Okay? So we'll jump right in here. Some of these are going to be really, really nice and easy, where they're just going to give us an equation and ask us to maximize it or minimize it. So in this case, the problem says, find the number of units to produce maximum revenue, given that the revenue is 600x squared minus 0.02x cubed. Okay, real straightforward. We're given a revenue equation, and we want to maximize revenue. So all we simply do on an equation like that is we find its derivative. Okay, so I take r prime. Its derivative would be 1200 times x, because I times by 2. 3 times 0.02 is 0.06 x squared. And then I set that equal to 0. Okay, I can obviously factor out an x. Set that equal to 0. If I set both of those equal to 0 and solve, I get critical numbers of x equals 0 and x equals 200. Excuse me, not 200. That would be if I divided 1200 by 6. 1200 divided by 0.06 is 20,000. Okay? Now, obviously, 0 is not going to maximize my revenue. If I plug 0 into that equation, I get a revenue of 0. If I plug 20,000 in, then I'm going to get a maximum revenue there. We could do first derivative test. We could do second derivative test. For example, the second derivative for that equation is going to be 1200 minus 0.0 or 0.12x. If I plug 20,000 into that, the second derivative is going to come out to be a negative number, meaning it's concave down. So I have a relative maximum at 20,000. Or I could do the first derivative test. So we're going to maximize profit over revenue in this case, sorry, when we sell 20,000 units. Okay? That's about as straightforward as you can get because you're just given the equation. You just got to find its derivative, find the critical numbers, and see which one is your maximum. Okay? Second one here says find the number of units that produces minimum average cost given that the cost equation is this particular equation. Okay, now, key thing. It says we want to minimize the average cost. They're giving us the cost equation. This is not the average cost equation. Remember, the average cost equation, which we represent with C with a bar over it, is the cost equation divided by X. Okay? So that means I have to take the cost equation over here, divided by X. Now, since I've got a fraction divided by X, I'm just going to take this equation and times it by 1 over X. Okay? So my average cost equation, now since all of the numerators have an X in them, I'm just going to take X and cancel out with one of the X's in all of the numerators. So I have 2x squared minus X plus 5,000 all over X squared plus 2,500. And there's my average cost equation. Now, to minimize that, I'll find the derivative of the average cost equation. So low d high, which would be 4x minus 1, minus high, $5,000, d low, which would just be 2x, all over low squared. Okay, the top, I'm going to get a 4x cubed there. Over here I'm going to get a 4x cubed, and this one's a plus and this one's a minus, so they're going to cancel out. I got a minus x squared. Over here I have a minus 2x squared. But the minus 2x squared is going to become a positive because I have a negative minus that. Okay? So we have a negative x squared plus 2x squared, 1x squared. All right? 2,500 times 4, we have a 10,000x. Over here, we have a 10,000x. 10,000x there, minus 10,000x there, they're going to cancel out. Minus 2,500. So that's what my top cleans up to be. Bottom x squared plus 2,500 squared. All right. Okay, so the top factors into x plus 50 and x minus 50. So my critical numbers are x equals plus or minus 50. Nothing makes the bottom 0, so I don't have any critical numbers from the denominator. Obviously, we're not going to sell or produce negative 50 units. So my 50 units would minimize my average cost in this situation. Okay? So key thing again, watch for those terms average cost. Make sure before you take the derivative then, you take your equation and divide it by x to get your average cost equation before you take the derivative. All right, this problem says we want to find the price per unit that would produce maximum profit given the cost is 100 plus 30x and the price per unit, remember this little p is price per unit, is 90 minus x. We want to produce maximum profit. Okay? Now profit, remember, is revenue minus cost. Okay? So first of all, we have to figure out what our revenue is in this case. Now revenue is price per unit times the number of units, x times p. So I'm going to take my price per unit, plug it in there. So my revenue is x times 90 minus x. My cost is already given as this equation right here. So my profit equation is going to be, I'm going to go ahead and distribute that. It's going to be 90x minus x squared minus the cost equation, which is 100 plus 30x. Cleaning that up, I got a negative x squared. 90x minus 30x is 60x minus 100. And from there, then it's a real straightforward problem. revenue minus cost. My revenue is number of units times the price. So I plug that in, minus my cost equation, simplify it, and now we're ready to maximize that. So I'm going to take my derivative, negative 2x plus 60, set that equal to 0, and I get x equals 30. Okay. If I were to take the second derivative would be negative 2, which tells me this is always concave down. We have a parabola in this case, so it's a downward parabola. So that's basically the vertex of it, or my x-coordinate of the vertex. Now the question says, find the price per unit that would be charged. This is the number of units. I go back to my price equation, which is 90 minus x, and I subtract 30. So my price per unit that I would want to charge, based on that information, is $60. Okay? All right, let's take a look at this one. Okay. Example 4 says, when a company sells a product for $40, they sell 140 products a week. Okay? So there's my units sold. There's my price. When they increase the price by $4, okay, so we're going to change the price by $4, they only sell 134 products a week. Okay? So an increase of $4 led to a decrease of 6 units. Okay? If they increase the price by $4, they decrease the number of products sold by 6 because it went from 140 to 134. Each product cost them $23 to make. Okay? So my cost per unit is $23. Okay? Assuming the demand is linear, what price should they charge to maximize their profit? Okay. So what I'm going to do on a problem like this, remember, is profit is equal to revenue minus cost. First thing I'm going to do is I'm going to get a revenue equation. Okay? Now revenue is price times units sold. All right, so my price is $40, but remember the price is going to change on this problem. We're looking at how many times we should increase the price. So I'm going to start with a price of $40, but I'm going to increase it by $4, so I'm going to add 4 times x. Now, that x is not representing the number of units sold. X is going to represent, in this case, the number of price increases of $4. So, for example, if I get x equals 1 for this problem, that means I'm going to raise the price by $4. If I get x equals 2, I'm going to raise the price by $8. Okay? All right, the number of units sold. When they sell it for $40, they sell 140 units. But when we drop the price, or excuse me, when we raise the price, we lose 6 units every time we increase the price. So minus 6x. So if I raise the price by x equals 1, that would be $44, and I would only sell 134. If I get x equals 2, the price would be 48, but I'm going to lose 12 units sold, so I'm only going to sell 128 units. Okay? And so on. Okay, now the cost equation. All right, it costs me $23 for each product that I make. Now here's the kicker. Okay, you got to make sure here that you don't just do 23 times x, because x, remember, is not the number of units that we're selling. The number of units we're selling is this. So the cost is going to be 23 times the number of units sold, which is the 140 minus 6x. So that's going to get used twice in this problem. The number of units sold times the price is the revenue. The cost per unit sold, 23, times how many units sold. Okay? And then we know that profit is revenue minus cost. So profit is going to be this equation, the revenue, minus the cost. Okay? Now, whenever you do one of these problems, that means one of your binomials is going to be common. So I can take that out. My other binomial is going to be the 40 plus 4x minus the 23. So if I go ahead and do 40 minus 23, I got 17 plus 4x. Which, if you think about it, kind of makes sense. Okay? It's costing me $40 to produce a unit, but I'm selling it for 40, excuse me, but it's costing me 23 to make it. So my overall profit per unit is $17. Okay? And then I'm selling them, or I'm going to increase that by $4, but that's going to decrease these number of units here. Okay? All right. So you got two options here. When you take the derivative, you could FOIL this out and then take the derivative of that, or you could do the product rule and do the derivative that way. I'm going to FOIL it out first. Okay. So we've got 140 times 17, which I believe is 2380. And we've got 140 times 4x, which is 560x. Okay. In the middle, when we do 17 times 6, let's see, that's 60 and 42, so that's 102. So we're going to end up with 560 and 102. One's a plus, one's a minus. We're going to end up with plus 458x. And then we got minus 24x squared. Okay. Once I've got my profit equation like that, I'm ready to do the derivative. So derivative is going to be 458 minus 48x. I'm going to set that equal to 0. Solving for x. X comes out to be about 9.542, approximately. All right, now remember, this is the number of price increases. Now, your book sometimes is going to round the number of price increases to a whole number. Sometimes they use a decimal. Okay? So depending on what you round to here, if we say the number of price increases is going to be a whole number, then I'll round it up to 10. Now remember, my price per unit was 40 plus 4x, so if we're going to increase the price 10 times, that's going to give me $80 for the price I'm going to charge per unit. Or you might do this. You might say, oh, I can increase the price 9.5 times. So it's only going to be $78. And that's going to actually give me closer to my maximum. Because my maximum was 9.542. Okay? So we might do that and round it to 9.5 and say I'm going to charge $78. Okay? Just depends on how the problem what the problem says about how many your price increases, if it has to be a whole number or not. Again, don't assume the price increase has to be a whole number. You can round it off to the nearest tenth or something and get your price. We're going to charge $78 per unit. Okay? All right, so again with those, we got an original price, an original unit sold. If we raise the price, we just add that times x. If we decrease the price, which some problems might do, they might decrease the price, which is going to increase the number of units sold, and go minus there and go plus there. Remember, whatever you did for units sold is also going to be what you multiply the cost by, so per unit. So $23 per unit in this problem times the cost. So we end up using that same binomial twice in a problem like that. In some cases, they may just say on a problem like that, maximize the revenue. So you don't even have to do the cost. You just get your revenue equation and try to maximize that. Okay, last one here. Delivery companies trying to minimize their costs. It says find the speed V in miles per hour given the following cost for a 150-mile delivery. It says the fuel cost per hour is given by C equals V squared over 500, and the driver's paid $8.50 per hour. Okay? So both of these costs that are given right now are per hour. Okay? And we want to try to minimize the cost for this delivery. Okay? All right, so C, which is my total cost, is going to equal my cost per hour multiplied by the number of hours that's going to take to make the trip. Okay, my cost per hour, I have 2. Okay, my fuel costs, which are V squared divided by 500, plus the driver's getting paid $8.50 per hour. So those two things added together is what my cost per hour is. I then have to times that by the number of hours it's going to take to make the delivery. Okay? Now, trying to figure out the number of hours it's going to take to make the delivery, first of all, it's a 150-mile trip. Now, distance we know is equal to rate times time. So I've got a 150-mile trip. The rate I'm driving is v times t. So that means t is going to equal 150 over v. Okay? And everything's in miles per hour here. We've got miles per hour. We've got a mile delivery, so we don't have to worry about converting the units or anything like that. So the time it's going to take to make the trip then is 150 miles divided by my average speed. So the number of hours the trip's going to take is 150 over v. All right, once I got that, I'm going to clean that up a little bit. So I'm going to distribute the 150 over v in there. Okay, 150 over 500 is going to reduce to 3 over 10. V squared over v is just going to become v. And then we have 850 times 150, which comes out to be 1275 over v. So there's my cost equation. To optimize it, we've got to take its derivative. So 3 over 10 minus 1275 over v squared. All right, if I set that equal to 0, and if I move the 1275 over v squared to the other side and cross multiply, I'm going to end up with 3v squared equals 12,750. Dividing by 3 gives me v squared is 4250. Square root that. And v comes out to be approximately 65.192. So I'm going to say about 65 miles per hour. Okay? So if that's the situation for this delivery company, then we're going to tell that delivery driver as much as possible, try to keep your speed around 65 miles an hour. Obviously, they may not be able to do that the whole time, depending on traffic and things like that. But we want to try to keep them around 65 miles an hour if possible to try to minimize our costs for that trip. Okay? All right, so there's a few of the different economic problems you're going to see. Again, also make sure you read your book. Look at those examples as well. So they may do some different things there. Some different examples of things you're going to see in the section. Okay? So that's it for 310.